So picture a massive high-speed factory assembly line. Like everything is perfectly timed, perfectly choreographed.
Right, highly optimized.
Exactly. You have got this robotic arm, and it is programmed to reach out exactly every 3 seconds to grab a specific bolt and, lock it into a car chassis. But what happens if, for whatever reason, the bolt just isn't there on the conveyor belt?
Well, if the underlying system isn't designed to conceptually handle that absence, the robot arm does not just pause and ask for help.
Yeah, it doesn't have a brain.
No, it closes its grip on absolutely nothing. And then it swings that empty grip wildly into the machinery, smashes into the next delicate component, and the entire multi-million-dollar assembly line grinds to a catastrophic, sparking halt.
It is crazy to think about. The system was built for perfection, but the real world is inherently messy. Missing parts happen constantly.
All the time.
And when our systems, whether they are physical factory machines or, digital software architectures, when they do not know how to gracefully handle the concept of nothing, absolutely everything breaks.
It is a domino effect.
Which is actually a surprisingly profound place to start our discussion for this deep dive. Today, we are looking at a highly specific and honestly fascinating developer diary entry. It is titled Notes on Haskell Programming, Part 113.
Yeah, published by a developer named Ang on April 18th, 2026.
Right. And our mission today is to figure out how a tiny coding problem reveals these massive insights about problem solving.
And I want to set the stage right here at the start, because while we are diving into a snippet about Haskell programming, you really do not need to be a software coder to appreciate this.
Oh, definitely not.
Fundamentally, Ang's notes are about how complex systems handle the unexpected absence of information. It is about the eternal trade-offs between clever shortcuts and solid, reliable manual work.
So it is a philosophy of problem solving just as much as it is a coding diary.
Exactly.
Okay, let's unpack this. We begin at the exact point of friction that Ang experienced in the project. Ang was trying to add an index metadata field to set keywords within a text file.
Basically, a way to electronically tag a document so it can be searched or categorized later on.
Right. To accomplish this, the system was instructed to look for a highly specific string of text. In Ang's code, that marker is a specific Chinese phrase that translates to index, followed by a colon.
Yeah, the system's job, specifically a piece of code called a parser, was to scan through the document, find that exact text marker, and then read the keywords that immediately followed it.
But here is the problem Ang ran into. Initially, if the parser could not find this exact string anywhere in the text, it just flat out failed.
The bolt was not on the conveyor belt.
Yes, exactly. And the robotic arm smashed into the machine. Because it failed, the entire metadata field ended up being mistakenly treated as just a regular paragraph of text.
Wow, so the whole structure of the document just broke down.
Totally broke down.
You know, the fragility of that initial setup is something we see in poorly designed systems everywhere. The parser had an expectation of absolute perfection. It assumed the text file would always be formatted exactly right, with that specific marker present every single time.
But what if a particular document does not need any index tags? What if the field is legitimately, purposely empty?
Right, when a program does not have a formalized mathematical way to understand the concept of, hey, this thing might not exist, it attempts to process absence as if it were present.
Which is a recipe for disaster.
It leads to messy cascading errors, like treating back-end data tags as if they were front-end paragraphs meant for a reader.
Wait, so how does a programmer actually fix that? Like, how do you teach a machine that it is okay for something to be missing?
Well, the notes mention Ang updated the code to make this field optional, using something called the optional combinator. And this tool apparently returns what the Haskell language calls a maybe type.
A maybe type. Okay, tell me more about that.
So the maybe type is one of the foundational concepts in functional programming languages like Haskell. In a lot of older mainstream programming languages, if a variable does not have a value, the system assigns it a hidden default null value.
Okay, I have heard of null before.
Yeah, it is infamous. The danger there is that if you try to use that null value later in the code without realizing it's completely empty, your entire program crashes instantly. It is literally a trap waiting to be sprung deep in the machinery.
Hold on, I need to act as a proxy for anyone who might be skeptical here. Wait, so instead of fixing the missing data, Haskell just puts the empty space in a fancy box called a maybe type?
Sort of, yeah.
But how does that actually stop the program from crashing down the line? If the data is missing, isn't it still missing?
That is a great question. The data is still missing, yes, but the mechanism of how the language treats that absence changes entirely. Haskell forces the developer to be explicit.
What do you mean by explicit?
The optional combinator returns a maybe type, which means the value is now mathematically wrapped in a protective container. That container can only be in one of two states.
Okay.
It either says just meaning the data is inside, like just foobar, or the container says nothing, meaning it is intentionally safely empty.
Oh, I see.
And the reason this stops crashes is that Haskell's compiler, which is the engine that checks the code before it is allowed to run, will absolutely refuse to build the program unless you, the programmer, write instructions for what to do with the just scenario and what to do with the nothing scenario.
I think I am tracking with you. Let me try an analogy to make sure I've got the mechanics of this right.
Go for it.
Think of maybe type like a highly structured party RSVP system. You have got a bouncer at the door of the party that is our parser.
Okay, I like where this is going.
If a guest shows up and the bouncer expects every single person to have a +1, but this particular guest came alone, the bouncer panics. They do not know how to process a missing +1, so they shut down the whole party or like throw the guest into the coat closet.
A very chaotic, poorly planned party.
Exactly. But the RSVP card acts exactly like the maybe type container. It safely and explicitly states the reality of the situation long before anyone gets to the door.
Right, you check a box.
Yeah, you check a box when you mail it in. You either have a guest, which is just guest name, or you are explicitly coming alone, which is nothing. The bouncer sees the card, is legally required to read both options, expects the nothing, and smoothly lets you in single file. The party just keeps going.
That perfectly captures the mechanism. The bouncer cannot ignore the card. And if we connect this back to Ang's developer diary, we see this play out beautifully in the code.
How so?
Well, Ang's notes mention using the maybe function to check this specific variable. Then Ang uses the words function. The words function takes a continuous string of text separated by spaces and chops it up into a list of individual items.
Oh, okay, so it takes foo bar and turns it into a list that looks like foo and bar as separate tags.
Exactly. So it is breaking down a single long line of text into individual manageable tags.
Got it.
But here is the critical part and the answer to your earlier question about how this prevents crashes. Because Ang used that maybe wrapper, if the parser result is nothing, meaning that there are no keywords provided in the file at all, the maybe function elegantly defaults to an empty list.
Which is just represented in the code by empty brackets, right?
Exactly.
So it doesn't crash, it doesn't throw a fit or shut down the assembly line. It just says, no tags today, no problem. Here's an empty list of tags to pass along.
This completely neutralizes those cascading failures we talked about earlier.
Yeah.
By explicitly planning for nothing, the system remains completely robust.
That is so elegant.
The empty list simply flows down the rest of the digital assembly line, and all the subsequent machinery knows exactly how to handle an empty list. They just iterate over 0 items and move on. 0 sparks, 0 crashes.
So now we have this beautifully safe, boxed up data, but that creates a brand new problem in Ang's diary, doesn't it?
It sure does.
Because, how do you look inside a box without accidentally triggering the exact same crashes we just avoided? The next step in the notes is about outputting that data.
Right, Ang wanted to refactor and improve the debug output, essentially creating a clean way to print out each field of the metadata section to the screen, just to verify the parser was actually working.
And this is where Ang hits a very interesting wall, one that highlights a massive philosophical divide in the programming world. Ang notes that you cannot just loop through a metadata type in Haskell to print it out the way you would iterate through a dictionary or an object in a more mainstream language, like Python.
Let's define the contrast there. In Python, if you have an object or a dictionary, say a user profile, with a name, an age, and an index of tags, you can write a very simple 2-line loop.
Right, a very basic loop.
And that loop essentially says, hey, Python, look at this profile, figure out whatever is inside it, and print every single item you find to the screen.
Python just magically opens the filing cabinet, looks at every folder it finds, and reads it out to you. You don't have to tell it what the folders are called beforehand.
That is because Python is highly dynamic.
Yeah.
But Ang points out that Haskell data types are not collections in that sense. You cannot just blindly loop through them.
Right.
Furthermore, Ang notes that Haskell does not provide runtime reflection or dynamic inspection by default, which is the technical term for that Python magic you just described.
Wait, here's where it gets really interesting and where I have to push back again.
Go ahead.
If Python lets you just magically loop through any object and print whatever's inside it with 2 lines of code, why would a programmer voluntarily use a language like Haskell that actively restricts you from doing that?
Seems counterintuitive, I know.
Isn't the lack of dynamic inspection, this inability to just look inside your own data structure on the fly, a major step backward for developer efficiency? I mean, it sounds incredibly frustrating to have to manually map everything.
It is a common reaction when people first encounter a strict language like Haskell. It feels like you are being put in a straitjacket.
Yeah, exactly.
But this limitation is actually a profoundly powerful feature. To understand why, we have to look at the difference between how a language like Python executes code versus how Haskell does it. It basically comes down to interpreters versus compilers.
Let's break that down. How does the interpreter change things?
Think of runtime reflection, what Python does like a restaurant kitchen. Python is a highly skilled but entirely improvisational chef.
Okay, an improvisational chef.
The chef opens the fridge, looks at whatever ingredients happen to be there at that exact moment, and invents a menu on the fly. That is flexible, and you get dinner very quickly.
But there is a but coming.
But it is unpredictable.
Hmm.
If someone accidentally put a raw, toxic mushroom in the fridge, the Python chef might just blindly find it, chop it up, and serve it because they are just processing whatever they find at runtime.
Ah, so because Python is blindly opening every drawer in the filing cabinet and pulling out whatever it finds, you completely lose control over what happens next.
Exactly.
If someone accidentally sneaks a weird, unexpected piece of data into that object, Python's reflection will blindly find it, try to process it, and suddenly your debug output is printing sensitive user passwords to a public log, or crashing because it found a weird data type it doesn't know how to print.
Which brings us to the compiler. Haskell does not use an improvisational chef. Haskell operates a kitchen where the entire menu must be submitted, mathematically verified, and every single ingredient explicitly approved by the health inspector before the doors even open to the public.
Okay, so the compiler is the strict health inspector.
Yes, that health inspector is the compiler.
So the lack of reflection is actually a security and stability feature.
Exactly the point. By restricting runtime reflection, Haskell forces a strict design. By not having that dynamic inspection by default, the system completely avoids unexpected behavior.
Because it already checked everything.
The compiler demands to know exactly what is going to happen before the program ever runs. It trades the quick, magical flexibility of Python for rock-solid predictability.
I see.
If a Haskell program compiles successfully, you have a very high degree of certainty that it is going to run exactly as intended without any weird runtime surprises, because it simply cannot improvise.
Okay, so if that magic Python looping is off the table, Aang had to figure out how to actually print these metadata fields for debugging without it. And how Aang chooses to solve this is, I think, the most universally relatable part of this entire diary entry.
Oh, absolutely.
It tells us so much about good problem solving, far beyond just writing software.
Aang was faced with a choice that every engineer, designer, and really every human faces on a daily basis. Do I find a clever, complex workaround to simulate the automated magic I want, or do I just do the manual work?
And Aang chose to just do the work.
Yep.
The notes detail how Aang took a fully manual approach to printing the data. Instead of trying to force a loop, Aang wrote out exactly what needed to be printed field by field.
Right, explicit instructions.
The code shifted to a cleaner mapped approach. Aang wrote a function called print content, which maps a print command, specifically puts strln, which just puts a string of text on a new line across explicitly formatted fields.
The specific line of code Aang shares in the diary uses that mapm function. It might look a bit intimidating if you don't read Haskell, but the underlying logic is brutally simple.
What does it translate to in plain English?
It means take my explicit, pre-approved list of formatted fields and one by one manually apply the print action to them. No magic discovery, no improvisational chef.
Just a straightforward set of instructions.
Right. Print the title, print the author, print the index.
And Aang explicitly acknowledges the temptation to do it differently. The diary entry says, of course, there are other ways to approach this. However, from what I've gathered, those methods are quite hackish and introduce unnecessary complexity.
Hackish is the perfect word for it.
I love the use of the word hackish here. What does a hackish workaround actually look like in a system like this?
Well, a hackish workaround usually looks like a massive convoluted machine built to do a very simple job. Aang could have downloaded heavy, complex Haskell libraries specifically designed to simulate Python's reflection.
Just to print some debug text.
Exactly. Aang could have written dozens of lines of advanced, abstract template code to force the language to dynamically inspect itself against its own nature.
Well, it sounds exhausting.
And those methods create technical debt. They make the code significantly harder for another human being to read, harder to maintain when things change, and often slower to run.
Opting for the simpler manual approach is just cleaner. It gets the job done without fighting the architecture. And Aang notes that this manual mapping doesn't negatively affect readability or performance. In fact, it preserves them.
It is the hallmark of a mature engineer. When developers first start building systems, they want everything to be infinitely dynamic and automatic. You want to write one clever, magical line of code that solves every future problem forever.
We all want that magic button.
But as you gain experience, and as you suffer through debugging those clever systems, you realize that explicitly stating what you want a system to do, even if it takes a few extra lines of typing, is infinitely more valuable.
Because it's clear?
Someone else, or even you 6 months later, can open that file, read it from top to bottom, and instantly understand exactly what it does.
I think we can all relate this directly to our own lives, well outside of programming. How often do we spend hours, literally hours, trying to automate a simple task or find some convoluted shortcut when just doing it manually, the simple way, would have taken 5 minutes and been totally foolproof?
Oh, all the time. We gravitate toward over-engineering because building the complex machine feels like real work. We want to be clever.
Exactly. You spend an entire weekend setting up a complex, fragile ecosystem of smart plugs, Wi-Fi bridges, and voice commands just so you don't have to reach over and flip a physical light switch from the couch.
I feel personally attacked by this analogy.
Right. You introduce all these points of failure, and then a router update happens, the internet goes down, and you are literally sitting in the dark because you engineered away the manual switch.
Yeah.
You built a hackish workaround for a solved problem.
The smart home analogy is the perfect translation of what Aang is avoiding in the code. The hackish solution introduces unnecessary complexity and fragility into your living room.
Just to save, what, 2 seconds of effort?
Yep. The manual solution, just reaching over and flipping the switch, or in Aang's case, explicitly typing out the print commands, is robust, instantly readable by anyone in the room, and performs perfectly every single time.
So what does this all mean? Let's recap the journey of part 113 of Aang's notes, because we have pulled a lot of philosophy out of a very short technical diary entry today.
We really have.
We started with a brittle parser, right? A system that completely broke down and miscategorized data if it couldn't find the exact text string. It was a factory arm swinging at an empty conveyor belt because it could not handle absence.
And Aang solved that by introducing the maybe type. By mathematically wrapping the data in a structure that explicitly forces the program to plan for nothing, Aang prevented those cascading failures.
It is the RSVP card that tells the bouncer exactly how to handle an empty guest list without shutting down the entire party.
Perfect summary.
Then, moving to the debug output, Aang hit the wall of Haskell's strict compiler-driven design. Unlike Python, which uses dynamic runtime interpreters to magically loop through data on the fly, Haskell demands a pre-approved menu. It does not let you blindly open the filing cabinet and print whatever you find.
Finally, instead of fighting that strict design with complex, fragile, hackish workarounds to simulate Python's magic, Aang embraced the limitation.
Yeah, Aang wrote a clean, explicit manual mapping function to print the data. It was not a clever magic trick, but it was readable, highly performant, and incredibly robust.
This is a fantastic reminder that the boring, straightforward solution is very often the best one.
It really is.
You know, I want to leave you with a thought to mull over, something that takes Aang's appreciation for manual, explicit work and projects it into the future.
Okay, let's hear it.
We are entering an era where AI models are writing more and more of our code, but AI models operate by predicting the most common patterns, and they heavily favor those fast, complex, Python-style workarounds because they look clever and are easy for an AI to generate on the fly.
Oh, that's a really good point.
If we increasingly rely on machines that default to hackish, heavily abstracted complexity to solve problems, will we lose the human appreciation for the boring, manual, robust systems like Haskell altogether?
That is a phenomenal question. Are we training a generation of developers and AI tools to build fragile robotic arms that smash the assembly line simply because reaching out and placing the bolt manually isn't clever enough?
It's something we really need to watch out for.
Sometimes the most elegant system you can build is the one that simply plans for nothing, skips the magic tricks, and does the manual work without complaining.
I couldn't agree more.
Well, thanks for joining us on this deep dive. We will catch you next time.